All right, here we are for Honors Physics Worksheet 3 on electrostatics using Coulomb's law. We want to take a look at question 5, okay? And this is kind of another plug and chugger problem. It says a negative charge of 2 times 10 to the negative 4 coulombs and a positive charge of 8 times 10 to the negative 4 coulombs are separated by 0.3 meters. What's the magnitude of the force between the charges, and is it repulsive or attractive? You say, okay, we can do this. And so you say, well, oops. It's really going to follow the same format as the previous problem, isn't it? But so we'll draw it over from fresh. So you say, they tell us 2 charged particles. You say one is a negative charge and one's a positive charge. So let's see, we've got a negative, we've got a positive charge. They tell you that this is 2 times 10 to the negative 4 coulombs, and this one is 8 times 10 to the negative 4 coulombs. I guess this is a negative 2. Right? And they tell you that these 2 charges are separated by 0.3 meters. This is 0.3 meters, okay, between the middles of the charges. And they would like to know about the force. Right away, before you even do any calculations, you say, hey, I've got a positive charge, I've got a negative charge. Is the force going to be attractive or repulsive? And you say, well, sure, if I've got unlike charges, positive, negative, they're going to attract. That's the fundamental rule of charge. Unlike charges attract. So this will be attracted along the line between the 2. And this will be attracted that guy along the line between the 2. And of course, the force on this left charge because of the right charge has to be the same as the force on the right charge because the left charge is the same size. Newton's third law is one interaction between them, so it's the same on both. So taking a look at that, we're ready to go ahead and calculate that force. We're going to use Coulomb's law. Electrical force is K. First charge, second charge, over the separation squared. Plug in my values. K is 9 times 10 to the 9. The Q's, 2 times 10. And again, when I do this, I'm making it a positive value, right? When we do this equation, we just use the absolute values of the charges. Remembering that this equation can't tell you both directions at the same time. This equation just tells you the size of the magnitude or the size of the force, not the direction. Q2 is 8 times 10 to the negative 4. And then the distance is 0.3 meters. And of course, it's squared in the equation. So there we go. I like to take my, my coefficients out. 9 times 2 times 8 divided by 0.3 squared. Then do my powers of 10 off to the side. Negative 4 is negative 8 times positive 9. That's going to be just 10 to the first power. Okay, punch this in my calculator, and when I do so, 9 times 16 divided by 3 squared. Okay, this is going to come out to be a whopping 16,000 newtons is my answer. You say, hey, oh my gosh, compared to the last problem, oh my gosh, last problem was like 1 Newton, and this is like 16,000 newtons. You say, it's because, look, these charges are more like 100, they're 2 powers of 10 greater than the last one. Last time we had microcoulombs, now we have 10 to the minus 6, now we have 10 to the minus 4. You say, well, yeah, that makes sense, okay? If you're making the charges that much bigger, 100 times bigger for each of them, you'd expect it to jump up by 4 powers of 10, and that's exactly what happened, right? This is 100 times bigger. 100 times bigger would be 100 times 100, right? It'll be 10,000 times bigger, and that's what we're getting. Okay, cool. Okay, and that's problem 4. Problem 5. Problem 5. Problem 5. Yes.